Hello, hello, hello! Welcome back. It is still Tuesday, the 3rd of February. Welcome back to part 2. Doing a double today. So apologies as well, first of all, if you were expecting the stream to happen earlier. I even mentioned earlier today that I would be on at 5:30, and then naturally between my stream this morning and my stream now, 2 sessions got inserted/rearranged, and so now we're here at 7 p.m. But my plan for this is to go over some of the things that we did this morning on the experimental physics, really kind of thinking, I kind of like what we've got going now with these sort of like evening tutor seminar streams, which is kind of like, if you have a topic test tomorrow on this topic, what are the things you need to know in order to do well? I have this a lot with my IB physics students, for instance, like kind of finding all the topics. There's a lot to learn, not a lot of time, lots of subjects to do, and it can be very hard to kind of consolidate the core material. These will be your kind of primers on, all right, this is the most important stuff. If you learn nothing else, learn this and you should be fine. So what are the things today? Mainly 2 things. When it comes to the experimental physics, we've got 2 things going on. The first is how to take a model and turn it into a straight line, because that is all of experimental physics. Taking a model, converting it to a straight line, interpreting the gradient and intercept. So the skills for that are very important. We'll go through that. And we'll also then go through how to deal with uncertainties. So 2 streams in one day. Yes, 2 streams in one day. Well, because my Tuesdays have been pretty quiet. Also, I will say my student has set up a Discord server. I need to now get a Discord account so I can be added to my own server as an admin. But it was actually on the recommendation of a student that I did what I do today about the experimental physics. So I think it'd be good to, like, because I know I recognize you. You're the one who asked me for the Discord server. And so things like you know, getting people to recommend topics for me to go through, that kind of thing. Super happy to do that. And so today I'm planning on doing modeling into straight lines plus how to deal with errors, because I find that both of those are not necessarily very well taught in classrooms. People ask me about them a lot. So coming here in one place, getting it done, good way to go forward. So without further ado, also, as usual, if you are in chat, feel free to drop questions and I will answer them. So going to the Miro whiteboard. The main thing about experimental design is whatever model you have, everything is about the graph you draw. So a classic one I like to take, t is 2 pi root L over g. This is the time period for a pendulum. This is not a straight line. And so the very first thing you have to do is to think, what can I do with this that would give me an equation that would yield me a straight line? So you're going to square both sides. And then if I rearrange that, it's clear I have no control over g and 2 pi is a constant. So these are all constants. But what that means is that t squared is directly proportional to L. So L I can control. From this, well, first of all, if it's directly proportional, that means it should be a straight line through the origin. And we know the intercept will be 0, but we can also then say the gradient will equal 4 pi squared over g, which means if you do this experiment, you will be able to calculate g, which is quite a cool result. So thinking about turning it into a straight line and interpreting the gradient and intercept to find something. So now that we've decided what our straight line is going to be, we can begin to think about how to collect the data. So the thing we control is L. So that is the independent variable. Can't spell. It's because I want to rush through the word. And so, like, hold on, independent variable. And I'm like, no, get to the end, get to the end. Like right there, I was like, get to the end of the word, wasting time. Hold on, so the independent variable is L. That's the thing we control. The dependent variable, the thing you measure, that is T. So what we want to do is to have our L values measured in meters, and we want to measure time. What we end up doing with this experiment is measuring multiple time periods, not just one, because by measuring, for instance, 10 time periods, so we're going to do 10 of them, and we're going to measure it 3 times per length. From this, we can get an average, and from that, we divide it by 10 to find the time period. And this is how you would set up your data table. Sorry, these should be in seconds. Always with the units. This is how you would set up your data table in order to collect the data to plot to find these values. I was able to do this after I worked out what straight line I was planning on plotting, because I cannot stress more highly how important that is in experimental physics. That is all about the straight line you plot. And then once we have our time period, oh wait, no, because that's not what we want. We don't want time period. We want t squared. So t squared in seconds squared, and then that would be the final column. I feel like with questions, you have to be careful because the x-axis could also be L to the half. Yes, it could, which is why, and in fact, it was so annoying in my stream this morning. There was an entire period where I had to like get a subscription to a thing so I could actually draw straight lines on the paper. But so I'll make sure to edit that out. But the main problem I had was read exactly the sort of technicalities of reading the question, that every question is unique. And if you just miss something, like I missed that there was a double y-axis graph. So I read both the intercepts off the same axis instead of actually looking on both sides. Little annoying things like that. You're right. These papers are so full of traps. So you're right. T against root L would also completely work. It's not typically how this particular one goes, but yes, you could do that. Okay, so that's one example. Let's do another example. Let's do, for instance, radioactive decay. Do I want to do that? I'm going to do a good log one. Why don't I cover, so for instance, another hypothetical we could do is Kepler's third, which I cannot remember off the top of my head. So, oh no, I'm going to have to derive it. We know that, hello, we got someone else in the chat. So for instance, let me just off the top of my head derive Kepler's third. So we know that the gravitational force, GMM over r squared, is equal to mv squared over r, where v is equal to 2 pi r over t, mv squared over r. So v squared is equal to 4 pi squared r squared over t squared. Plug that in, we get 4 m pi squared r squared over, nope, because that cancels with that. What am I doing? That's a T. Guys, I promise I can do physics. All right, so 4m pi squared r squared. Yes. All over RT squared. That cancels down, so just give me R. So by shifting this around, T squared, the M's cancel as well, equals 4 pi squared over GM times R cubed. So in this particular case, if we have a power law relationship like this, what we can do is take logs of both sides. So by taking logs of both sides, you can work out what the power law relationship is. So we know that, for instance, 2 log t is equal to the log of 4 pi squared over gm plus 3 log r. So if we were to plot log t against log r, it would be 3 over 2 log r plus a half log 4 pi squared over gm. And from this 3 over 2 of the gradient, we would expect to have a straight line with a gradient of 3 over 2, which would tell us about that power law relationship, and the intercept. So you could verify things you could do with this curve. You could verify that the gradient is 3 over 2. That's what you would expect. And you would get the intercept, whatever your data tells you the intercept is, that would be equal to a half log of 4 pi squared over gm. So if that intercept was c, for instance, what interesting thing could I do with this? I could use this to work out the mass of whatever this star or planet is orbiting, which is quite cool. Because 4 pi squared, just rearranging this, over gm would be equal to 10 to the power of 2c. And then rearranging to make m the subject of that formula, 4 pi squared over g times 10 to the 2c for whatever intercept you measure would be the mass. So again, using log laws, taking logs of both sides in order to work out a power law relationship. Realistically, this is not a practical you would do in the classroom, but this is just to give an example of something they could give you. You could also do something with logs, or like the natural logarithm. So let's say we were doing capacitor discharge, and it was something like V equals V naught e to the minus t over RC. We could also think about turning this into a straight line by taking natural logs of both sides. Ln V equals ln V naught minus t over RC, which means that a plot of ln V versus t should have a negative gradient, and the intercept would be ln V naught. And the gradient would be equal to minus 1 over RC, from which you could work out, for instance, the capacitance that you're using. So much of this is about taking the model, taking the equation that you know from the syllabus, and turning it into a straight line and interpreting the gradient and the intercept. So that is one very important idea in all the papers like this. And the second thing that people really tend to hate is how to combine errors and uncertainties. Now, the best way to do this is really just to, well, actually, I'll lay out the rules first. This may be standard hat for some of you, that's fine, but I'll still lay it out. So if you are adding or subtracting values, then you add the absolute uncertainties. Come on, you can do it. If you are multiplying or dividing values, you add the percentage uncertainties. And if you are taking a value to a power, then what you do is you multiply the percentage uncertainty by n. And I think the best way to demonstrate these rules is to do them in practice by coming up with a bunch of random numbers. So let's say that A is equal to 1.07 plus or minus 0.03, and B is 12.9 plus or minus 0.9. We could work out, for instance, what B minus A is. the first thing I'm going to do is to work out what the sort of core value would be. It would be 12.9 minus 1.07, which would be 11.83 if we ignored the errors. And now, because we are subtracting values, that means adding the absolute uncertainties, which would be 0.93. So the absolute, let's do this separately. The absolute would be like 11.83. And then if we take the uncertainties, the absolute uncertainty would by itself be plus or minus 0.93. But the very important rule with uncertainties is they should be to one significant figure. So that means I'm not going to use the 0.93. I'm instead going to use plus or minus 0.9. And then that sets my precision for this value. If this is 1 decimal point, then this should also be 1 decimal point. So this becomes 11.8 plus or minus 0.9. So now let's work out what that would what would happen if I multiply values. So let's say I had, or rather, let's do b divided by a. No, let's do a divided by b because that looks like it'll be uglier. So a divided by b. If I were just to plug the numbers in, 1.07 divided by 12.9, I would get 8.29 times 10 to the minus 2. And what I'm going to need to do is to work out the percentage uncertainties in these. Because I'm dividing the values, that means I'm adding the percentage uncertainties. So the percentage uncertainty in A is 0.03 divided by 1.07. And that is 2.8%. Now I'll let this be to 2 significant figures without any issue, because like this is working on the way. I don't want to sort of accumulate a bunch of rounding errors. And the percentage uncertainty in the second one is the 0.9 divided by 12.9 times 100. So this is 7.0%. So if I'm adding so the percentage error here is going to be 2.8 plus 7.0. So it's going to be 9.8% uncertainty here. And I need to work out 9.8% of the true value that I calculated. So if I take this, add my 2.8%. Oops. Did I do that? Yeah, nailed it. So that times the 8.29 times 10 to the minus 2 I found earlier times the 8.29 times 10 to the minus 2, that gives me an uncertainty here of 8.1 times 10 to the minus 3. So in other words, this would be 8.29 plus or minus, oh no, this would be 8. What I'm going to have to do with the standard form, that's going to be plus or minus 0.8, and this will become 0.3, and that will all be times 10 to the minus 2. We have a question. Oh, Mudasar! Yeah, I remember you. Oh, you got your Oxford offer. Yes, thank you very much. Yeah, you took some interviews. You did good. So I maintain, yeah, you got yourself that offer, man. So now it's all the sort of challenge for you is to meet the offer. No, but you're very welcome though. Right. So this is what you would do when you're sort of dealing with standard form as well. And the final thing I want to do for this set of numbers before I sort of change it up is let's consider what, I don't know, because I've picked up very low numbers, so this will not be meaningful if I actually take powers of it. But let's take b cubed over a. Why not? So if I'm considering b cubed over a, let's work out what the core value, like the sort of the basic value would be. So it would be 12.9 cubed all over the 1.07. And that would give me 12.9 cubed all over 1.07 is 2006. But what we're going to have to do is for the percentage errors, we're going to add the percentage error of the b cubed plus the percentage error of the a. And because that's b cubed, the percentage error in it is 3 times the percentage error in b by itself. So the percentage error there is going to be 2.8% from the a plus 3 lots of 7. Damn, that's going to be big. Plus 3 times 7.0. So that's obviously 23.8%. So working out what 23.8% of 2006 is, it's equal to, in one significant, it would be equal to 477. And then in one significant figure, that would be 500. So in other words, the final answer for b squared over, for b cubed over a would be 2000 plus or minus 500. Ooh! Minusar, very well done. 88 out of 100 on the PAT score, because the PAT is not easy. I've complained about it on like every single live stream that it's come up on, because it's like so weird the fact that you couldn't really practice on it because it went from long form to multiple choice. They never released proper past papers for the multiple choice. And from what I've heard on a stream, they're getting rid of it entirely and replacing it with the ESAT across the board. So well done for doing that well on a PAT test. Like, I can definitely see why the offer was inbound from that. Crazy score. 88% on a PAT test. Like, hang it in the Louvre. That's spectacular. Yeah, people getting into Oxford while scoring 30 in PAT is insane, though. Like, I have no time or patience for the PAT, and apparently I no longer need to because I think it's dying a very hard-earned death. Right, let me just run a bunch of, let me do a different set. So if it was like 3.9 plus or minus 0.7, and B is, let's say 102 plus or minus. Let me think of it. Is there anything that's I really want to cover? Because I think, actually, before I go into this, let's talk about what happens. Because the thing I've been saying is that uncertainties should be one significant figure, and that it should agree to the same precision as the main value should agree with the same precision as that. There's some uncertainty on my end as to whether, like, for instance, if I had like would something like this be allowed? So I have a thing. My thing is, if it rounds to 0.1, you are allowed to include a second significant figure. If it's 0.15 or higher, then I would just call it 0.2. But I wouldn't really round down. I would kind of leave that as 0.12. So I'll leave it as that. And then I'll call this, maybe to make them a bit more even, 10.2 plus or minus 0.8. Before I get into this now with all of these numbers, someone is in the chat. I recognize you as well. You don't take further math. Do you recommend doing further math on your own before going to Cambridge for NatSci, or it isn't needed? It is true that you do not need to do it because they do teach you further math while you're there. I will say, depending on what you want to do, remember there are 2 streams for math. There's math A. Well, yeah, if you're doing I assume if you're here, you're not talking about doing biology. You're talking about doing physical natural sciences. Remember, there's 2 streams. There's math A and there's math B. I would recommend you doing math A, which is the lower stream, if you haven't done further math. I did do further math. And I started off in Math B, and then I dropped down initially because I got kind of put off because everyone seemed to be getting it really quickly, not realizing that it was a further math topic that all my peers had done because they'd done further pure and I hadn't in my school. So the fact that they were ahead of me gave me a sort of weird complex about my own math ability. So that's the one reason you might want to sort of do a bit of reading just to get a little bit ahead. Feel like because psychologically, you don't want to start off feeling behind. But I would recommend if you're not doing further math, start off on the Math A stream and they go through all the further math content in that. Yeah, like so many Phys NatSci offers study further math. Have they? Well, clearly not. Okay, so the obviously don't know names, but Ugla4, if you kind of let us know, are you on the Bio NatSci stream or are you the Phys NatSci stream? Honestly, like if you have a bunch of options, so for anyone sort of not in the chat right now, hello. For anyone not in the chat right now, we were sort of discussing you're a physical NatSci. Okay, so that's really interesting doing Phys NatSci without the further math. Is this basic physics? This is a continuation. I recognize you from this morning. So this is a continuation. This is the sort of core theory we're doing of experimental physics. So we're talking about turning things into straight lines, and we're talking about error analysis. But right now, I'm sort of answering comment questions about entering Cambridge and sort of how to prepare best for that. So, comment question. In fact, if I'm answering comment questions, I should stop sharing screen. So, if you are in the so in the summer, you've got a couple of options: coding or study further math. Honestly, if I had an option like your further math. I would say if you didn't do further math, there's no bad option here, right? There really is no bad option here. Because your further math will be taught to you in Math A regardless, I would 100% recommend doing Math A if you haven't done further math. You do also get a little bit of coding prep. This will definitely have advanced since I did my degree. But when I was doing it, we had what were called MATLAB projects. So we didn't do full like sort of Python coding or C++ or anything. We did it in something called MATLAB, and oh God, those were awful. We had 3 MATLAB projects in first year, and we had to do like a full project with a full write-up, everything. And I just hold in your head what you think they were marked out of for like a full piece of coursework. Because they were marked out of 2 in half mark increments. And it was just so bad. But I imagine that the coding is advanced somewhat since 2012. And so I imagine they probably get you on some proper coding now. But why is there a choice? I think, let me put it this way, in terms of like formal stuff, coding could be fun. Further math, you can kind of read up on your own. You don't need to study like the full further math content. I would say there are certain things, maybe get your hands on CP1, CP2, like the further core material. Maybe you sort of brush up on a bit of that just for some security. To me, the coding seems more practical and also more future-minded. Sort of getting into coding now, obviously, it's like not just good for sort of any sort of computational programming stuff, but it could be good for like, for future career stuff. So to me, I might lean more towards the coding if it's something you're interested in. But if you're feeling insecure about where you are, like compared to your peers entering the system, then maybe for peace of mind, you go for a further math. So up to you. Python is fun. Oh God, guys. If you've got a brain for coding, kudos to you. I am not one of you. I am not your people. I hate coding with every cell in my body. Like it just no. Like I love a good logic puzzle, but to do it relentlessly for an entire career, like no, my brain gets I just spit it out. I reject it. Imperial application. Which topics in further math are the most difficult? I can only study those. It's not about being difficult necessarily. It's about having the good foundation. I would say the let me have a quick look. I'll open up the further math textbooks. And I'll have a look at what I think are the most important for going into Cambridge NatSci specifically. So I would only open CP1 and CP2. I'm not going to share them on screen because obviously you have to pay for them, paywalling. I'm not going to get in trouble. But just scanning through complex numbers would be really good for you to practice. Volumes of revolution. Proof by induction. Vectors. And differential equations. Both first order and second order. I would say those 5 topics would be the ones to go for if you had any option. So rather than do the whole further math syllabus, those 5 topics, you'll have a really solid foundation. The rest of it you can learn there. And to be honest, those 5 you do learn there, but just sort of loosening the jam jar might give you a bit more confidence on that. All right, so keep the questions coming if you have them. In the meantime, I'm going to go back in and do a little bit more of the sort of error analysis stuff that we were talking about. I'm going to pop you guys back over here, and let's get going on another set. I'll keep an eye on the chat, obviously. So here, let's take this set of numbers and think about combining them in some sort of way. So in this case, let's take... can you tell you how you can learn the calculus fundamentals the easiest way? So calculus fundamentals, let's have this chat. Can you please explain quadratics? Definitely, maybe it like, okay. Let me think about the first question. So how do you get into calculus? I think the first thing you've got to do is simple polynomial differentiation. I teach it a slightly different way, where some people start teaching it from first principles. I don't like that. I think if you just learn the rule for differentiation and then learn how that applies to the gradient of a function, that's a good place to start. KK, can you explain quadratics? Yes, I can explain quadratics. I'm going to do that at the end, though, after I've done the error analysis stuff here, just because like that's sort of the bulk of this, and that's more of a side topic, but I will cover it at the end, I promise. Planning on being done sort of by 8 p.m. So if you're willing to hold on for about 20 minutes or so, maybe 15, 20, you should be fine. In the meantime, you can pop down what specific part of quadratics you want to go through, be that sort of like factorization, quadratic formula, something like that. Let's see. Vectors at university. I actually don't agree that vectors at university was extremely hard. I think if you understand vectors at further math is extremely hard, but I don't think that vectors at uni went that much further than that, to be honest. Because in further math, vectors is all about knowing your case studies and procedures. So it's things like intersection of 2 lines, intersection line and plane, distance from point to line, distance from point to plane, reflection of point in line, reflection of point in plane, reflection of line in plane. And almost like a surgeon, every single one of those has like a specific case study. Distance between skew lines, angle between 2 lines, angle between line and plane, angle between 2 planes. Just all these different combinations have their procedures. And almost like being a surgeon, like I do this step, then this step, then this step for like an appendectomy. Same thing for vectors. If you just know your case studies and know your procedures, you're fine. So it's not too bad there. So someone's requesting. Yeah, I would agree with that. I don't think the university vectors are that much harder, to be honest. Quadratic formula, since the complex and simple roots trip me up. Okay. Someone says, Oxford conveniently have all their math lectures and notes available to the public. did not know that. I know Cambridge was very much behind a wall. So you're going through them now. That is very convenient. I like that. Go Oxford. All right. So let me do one more set of the error analysis, and then we'll come back to some comment stuff to wrap. So here, if I want to do, for instance, a plus b, I would think about what the sort of the 10.2 plus the 3.91 would give me 14.11. The error would be 9 plus or minus 0.92, but I'm going to round that to one significant figure and say it is going to be 14.1 plus or minus 0.9. So I like to do the value and the uncertainty separately and then combine them at the end with appropriate significant figures. Considering what a times b is in this instance, 3.91 times 10.2, you would get 39.882 to full precision. Let's work out these percentage uncertainties. So 0 for A, so the percentage error in A would be 0.12 over 3.91 times 100, which when I run that in the calculator gives me, could I think about getting a calculator emulator? Yes, I could. Do I think that would be entertaining? No, I do not. So about 3.07%. And the percentage error in B is given by 0.8 over 10.2 times 100. So 0.8 over 10.2 times 100 would give 7.8%. So if I combine these percentage uncertainties, I would need to add them because these quantities are multiplied. So adding them together, you would get 10.9%. So 10.9% of 39.882 gives me, there we go. I can press buttons. It would be 4.3. So my final answer here with appropriate rounding would be 40 plus or minus 4. One significant figure in the error, same precision in the value. The final thing I might cover, again, I really shouldn't have chosen 10.02, like these ones that are very close to ones and tens, but my brain is doing what my brain is doing. So let's do, this could be fun. This could be fun. Let's consider a squared over the square root of b. So a squared over root b. Well, if I consider just the core values, it would be 3.91 squared all over the square root of 10.2, which gives me a value of 4.79. Now let's think about how we would combine these uncertainties. That's a squared, so I need to double the percentage uncertainty of A. That's root B, which is B to the half, so I have to take half the percentage uncertainty of B, and then you have to add those together. So in this case, the percentage uncertainty would be 2 times 3.07 plus a half of the 7.8% for B. So got another person in the chat. Hello, Technoburst. So 2 times 3.07 is 6.14 plus the half of 7.8 is 10%, basically 10% on the dot, 10.04%. So the 10% of this, when I run that through, multiplying by 4.79, you get, unsurprisingly, about the same, about 0.48, which I'm going to round up to 0.5 for appropriate number of significant figures, and it would be 4.8 plus or minus 0.5. So hopefully that gives a good sort of practical application for percentage uncertainties. Now, one thing I also really want to recommend when you're preparing for any practical paper is to memorize your core practical procedures. So every syllabus has some core required practicals that you're required to do in order to progress. And I recommend learning those protocols because in those protocols, they will have steps to reduce the uncertainties. And there's always some questions in the paper about how to practically go about reducing things like parallax error, or doing things like taking the 10 oscillations and dividing by 10 to reduce the uncertainty in the time period of oscillations. Things like that. And so it's worth, if you've revised those going in, you'll always have those ready to hand for how to reduce errors and improve experimental sort of accuracy. Right, spending time going back to the chat for a bit. Okay, so apparently not all of the math lectures for Oxford are online. I wouldn't think they would be. So the first lecture of each course online, apparently. MIT has everything online, though. You can learn a degree on your own from MIT Course Openware. Yale has a lot of free courses, too. That's interesting. Oxford defo have other year lectures for math. Never heard of other courses online. Yeah, the US might have stuff. Right. That, I think, is the core of what I wanted to go through when it comes to that, the experimental physics. I have had a specific request for some work on quadratics. This is more of like the GCSE stuff. So if it's not your jam, feel free to drop out. Alternatively, if you wanted me to go through something specifically in the next 15 minutes, feel free to drop it in chat and I'll pivot. But since there is a specific request, let's go through. So I had a request for want to do quadratic formula since the complex and simple roots trip me out most. Well, this is technically in the A-level syllabus, so in case you need any revision, I'm willing to do a little bit on that. So, in fact, I know people like my cousin really just like having me on in the background. Apparently, I'm very calming presence, which is the exact opposite of what I feel on the inside. So it's really good that I'm managing to try to transform that for all of you. But let's go through some quadratic stuff. So when you're talking about complex roots versus simple roots, as you put it, that's getting onto an A-level topic. So we know if you've got ax squared plus bx plus c equals 0, we know this is the form of a quadratic equation. If you ever do not have it in this form where it's equal to 0, I recommend rearranging it so it is equal to 0, because this is the form you need it in order to apply the quadratic formula, where x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now you will know that the square root, you can only take the square root of a positive number. So one of three things is going to happen here. Either this thing in the square root is going to be bigger than 0. Have a good night. So either this thing is going to be bigger than 0, in which case you will get two solutions, one from the plus, one from the minus. Or this thing under the square root will be equal to 0, in which case that will just be plus or minus 0. So you will only get one solution. And the alternative is that this thing in the square root can be negative, in which case you get no real solutions. That's why this thing in the square root is so important, and we give it a name of the discriminant. So b squared minus 4ac is the discriminant. And in the case, so if this discriminant is bigger than 0, we get two solutions. In the case where d is equal to 0, we get one solution. In the case where d is less than 0, we get no solutions. No real solutions, I'll say. Because it is absolutely true that you can use this, if you are familiar with complex numbers, theoretically, you could use this to get the roots in terms of I. There's also the other heinous formula, but I think it's like blah 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 blah. Do I want to go inviting heinous other formulas into my life? I don't think. I don't think. What I think, isn't there a formula for like the solutions of a cubic? Am I making this up? I might be making this up, but like, yeah, the sort of nice, safe, shallow waters of the quadratic equation are where I like to swim nowadays. It's not worth remembering because some cases don't work. Yeah. Yeah, there's a cubic formula. Yeah, I just don't. It's kind of like the divisibility rules for 7 and 11. Like, theoretically, I could commit them to memory, but also like, why? No, I don't want to. Yeah, cool. All right, so that's your quadratic equation. Let's come up with cases. So how do I let's make say really big. So let's say we got something like so if you're talking specifically about like because the comment specifically referred to complex versus non-complex. So let's come up with one. So if it has no real solutions, so let's say we had a quadratic that was doing this. Let's say I made my minimum point here -2, 3, right? We know from vertex form, I'm just going to make it nice and simple. We know this would be of the form x plus 2 squared plus 3. And I can expand all of this out and get x squared plus 4x plus 7. So if we were trying to solve, for instance, going a bit more into the further math syllabus now, if you had something like x squared plus 4x plus 7 equals 0, and you wanted to solve that for complex solutions, you could still use the quadratic formula. You could say that x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, which would be minus 4 plus or minus square root of minus 12 all over 2, which would be minus 4 plus or minus 12 is equal to 2 root 3. And that would be I, the square root of minus 1 all over 2, which would leave you with minus 2 plus or minus root 3i. This is sort of tying in further math complex stuff, if you've seen that. Now, I think I know that this commenter said this morning that you're in year 10, so I think you're looking more for the simpler GCSE version of this, in which case the quadratic formula, if you ever get a quadratic equation equal to 0, the quadratic formula is always there to help you find real solutions if they exist. But sometimes you type it into your calculator and you get a math error. And if that happens, that's this. That's the fact that the thing in the square root is less than 0. And so you get no real solutions for it. However, if there are real solutions, your calculator should always give it to you. And depending on the calculator you have, you might be able to just type the quadratic equation straight up into your calculator and it will solve it for you. So a lot of people find that helpful. But if you're still like sort of learning the ropes and you want to build up the strength of that technique, I would highly encourage you not to be using something like a graphics calculator that can do the work for you. Take the stairs, put the work in, keep it hard, keep it difficult, and then you're going to get more benefit from that work. So if you have something more specific you want me to go through, feel free to drop that in chat if that hasn't answered the question in the way that you want it to. But apart from that, I might spend a bit of time in chat, but we might end a little bit early because I know I just really wanted to keep today about those 2 core ideas from the practical physics, because I know that sort of different boards require slightly different things. And I think as well, practical physics tends to be a really difficult paper to prepare for because a lot of times they give you questions you've never seen before. Oh, someone's in chat. What does it mean? It's an imaginary number, but what is it? Oh, theoretical nonsense. Get to further math. What it's one of those things where I'm very good, like, working with imaginary numbers or complex numbers, but I'm really bad at explaining what it actually means in practice. Um, I would say don't get too far ahead of yourself. Now that you know this is there, complex numbers and imaginary numbers are there to look forward to. I will introduce to you the concept of I, which is the square root of -1, and then everything else can be done from that. In the same way that root 12 can simplify to 2 root 3 by taking out the square, which is 4, you can do a similar thing and take the square root of any number that is negative by taking it as, so for instance, the square root of -12 is the square root of 12 times the square root of -1. So that square root of -1, which we call I, is very important for taking the square root of any negative number, which is important to do in some instances. Now, I would also caution you that that is something that you only really get introduced to in the further math syllabus of A level, and I do not advise skipping steps. You want to make sure the math at every level is rock solid before you move on to the next level, because I still have students in like GCSE and A level who suffer with fractions. Like it's not great, and so like if you're skipping steps and if there are holes in the more foundational level of your math, that can cause structural instability when you try and build on top of that. So what I would advise you to do at this stage is to master quadratics at the level of the syllabus that you're at, so that by the time you put more work on top of that, then you're like, bam, got this, good to go. Oh, yes, I do know how I said I might speedrun GCSE papers during ESAT time. That's the summer. That's going to be so much fun. In fact, I did not just say I've got plans for this. Not only do I want to speedrun GCSE papers, I want to speedrun them mental math style. I want to speedrun them with my hands on my head, so you know I'm not actually writing anything down, and just see if I can get through an entire paper, non-calc, mentally. That'd be so much fun. Can you recommend using only GCSE techniques? Ah, you can recommend that. Although I definitely think this is curious. I'll take your feedback on this, because my whole hypothesis here is that people for GCSE are not going to be YouTubing for support as much as people for A-level will. GCSE is actually earlier than GCE. So GCE is basically what you call A-level. So this would be done in your final 2 years of high school or secondary school. GCSE in the UK system is sat in the sort of around year 16. So a classic example would be if you've read the Harry Potter books, your OWLs are GCSEs and your NEWTs are your A-levels. So there's ones that you sit in your final year. There's ones that you sit in your, if you're American, sophomore year, something like that. Yeah. Now, actually, I'll take your feedback on this. So when it comes to those GCSE papers, I think that most people at GCSE level are not. Maybe they are. Do you reckon GCSE people are like YouTubing for stuff? Because I've been trying to keep my stuff to A level on the basis that I imagine like you're more in charge of your learning process and more likely to be seeking out independent support. Because what I'm thinking is like the way you would approach a GCSE math paper if you're preparing for ESAT is so different than if you're in year 11 taking it for GCSE. Like if I was doing a live solve for GCSE students, I would be doing it nice and slowly, explaining how I'm going through all my steps, explaining how to lay it out on paper, because it's the first time you're doing a GCSE, first time you're doing a proper exam. There's like a nice way to go through it. Here's some exam technique. Here's how to go back, check your answers, make sure you're reading the question. And then if you're doing it for ESAT, I'm like, get out, go, answer, done, next, don't care, easy. And like, it's like communicating to wildly different audiences. So I'm not sure how accessible my speedruns would be to someone doing GCSE, but they would be wildly entertaining nonetheless. Your group of friends like the idea of speedrunning GCSE math papers in year 11, like sub 30 minutes. It's fun. Hey, maybe, yeah. Do you want to, if you're going for like a level 9, then speedrunning it could just be fun anyway. Just challenge papers. but also if you got to a point where you've mastered the syllabus, you've got to set yourself new challenges to keep things like alive and interesting. Okay. I mean, it sounds like good fun. Using only GCSE techniques. I would only use GCSE techniques anyway, to be honest. KK, so I'm explaining, so GCSEs, for anyone wondering, this is, we spoke this morning and you sort of, I think you might be outside of the UK system, but sort of also like in an earlier stage of the sort of system anyway. O levels don't exist anymore in the UK system. So let's say if you're using like the American high school system as a sort of reference point, then you would have your first year, you start when you're 14, your second year, you start when you're 15. At the end of that second year, you would sit GCSEs. So it's easier content. It's sat earlier in your education, and you sit them across a wide range of subjects. Then in the UK system, once you get past GCSEs, you move into A levels, where you specialize in typically 3 or 4 subjects, and then you sit your papers when you're 18 at the end of your full schooling. They still call them O levels in Asian countries. That is interesting. That is very interesting. Because I did see that O level still existed, and I always wondered why. Because this is the sort of my parents' generation got their O levels, and now I got my GCSEs. So I'm just sort of curious about that. So hopefully that answers those questions. Definitely. So one thing I want to do when I set up this Discord server, like I say, there are people who are invested in what they want to see from the channel. There are people who say, like, do some stuff on experimental physics, which is why I did everything I did today. And if you've got ideas of things you'd want to see, then it's like, at least I know at least someone's going to be engaged. So yeah, I think setting something up where I can kind of give people a bit more advance notice about when I'm going to go live, and also set something up where you can kind of submit questions you might like me to solve, for instance, if they're particularly challenging or interesting in some way, or particular topics you want to see me cover because you kind of have a test coming up, or you've got it's just a particular challenge for you and you want to get it done now and not leave it till the summer. Like, I'm very open to that feedback. Like, for me, tutoring normally is like people come to me and bring me something they want to go over, and I'm like, great, okay, I'll do that. And so that's one of the reasons I'm a tutor as opposed to a teacher. Like, lesson planning, not my thing. So if you guys have recommendations, I'm always willing to listen to them. Yeah, someone saying that Singapore and Malaysia still have O levels. Fascinating. But right, I'm gonna call it there. It's been a good solid hour. And do you know what, guys? This is how I like to do a stream. I really like sort of coming on, having a little bit of prepared content, going through demonstrating some of the skills, but also just going off and just taking like wild tangents, because that's the most fun part, is the interaction part, which is why, again, I'm doing streaming and not like prepared YouTube channels, or like YouTube videos, which I think I would personally find so dull. But right, I think we're going to leave it there. Thank you very much for joining this evening, and I shall be live probably, well, not the same time, but certainly sometime next week. TBD on whether I'm going to permanently swap to Tuesdays. So it's going to be sometime in the either like 5 to, it's realistically probably still going to be on Wednesdays at 5:30. It is going to have to be sort of dependent on my schedule and like how things are, and my schedule is like super flexible, kind of flexible. But I'll make sure to give you guys enough notice. Oh, what was this live about? Great question. This live was about, well, nominally, this live was about experimental physics. So I started by talking about how you take an equation from your physics book or from your formula sheet, rearrange it into the form of a straight line, collect the data to plot the relevant graph, and interpret the gradient and the intercept to get out physical values. That is a really important idea in a lot of your practical physics papers. The other thing I talked about was error analysis. So combining errors when you are adding, subtracting values, multiplying, dividing values, and taking values to a power. Because combining uncertainties is something that a lot of students have difficulty with, and I have found historically is not the best taught in classrooms. So that's what I went through. Yeah. Brilliant. And with that recap, actually, apologies that you've only joined right at the end, but I am leaving now. So hopefully you can catch it on catch up. Do you have any advice on how to choose like the axis scale quickly? Brilliant question. This is why we have people in chat to ask me questions, to remind me to say the important things. Okay, so you want to pick a scale that enables you to use, that you want your data to cover at least half of the slots, right? So let me show you, because there's also to truncate or not to truncate, that is the question. So I will, this is important enough, I'm actually going to dip back and show you this. So, okay, also, do not choose silliness for your axes. Do not choose multiples of 3. You want to be choosing something where the increments are nice, regular increments. So let's say my data runs between, if my data runs between, like, so like a classic 10, 20, 30, great scale, nice regular. 2, 4, 6, love. Nothing divisible by 3. 3 is a nice regular. Get out. No, 3 is not a regular increment. It doesn't subdivide. The point of these is that every little subdivision should be a nice thing. So no 3s, no multiples of 3. So your classic 1, 2, 3, 4, your 2, 4, 6, 8, your 4, 8, 12, etc. You can do your 4s. Doing 8s, not great. Wouldn't recommend, because that's when it starts getting bad. So these sorts of regular things. Now, what if your data only exists? So ideally, you would have it such that it goes through the origin. But basically, what you don't want is a graph where your data points are all bunched up. So you don't want a graph which looks like this, where you're only using like a very limited. So this might be a graph of V equals epsilon minus IR in physics, right? This wouldn't be a great use of axes. Because it doesn't use, I think the classic rule is you want your data to cover at least half of the available axis. So in a situation like this, rather than use a scale like this, which is forced starting at 0, you would choose to truncate it. So in this case, it is perfectly within your rights to truncate the axes and start not at 0. So let's say this was like between 30 and 30, 40, 50, something like that. You would be perfectly within your rights to change that so it starts at 30 and goes up to 50, and then the values do much more of that, because then you can interpolate much more between the values and get much more accurate readings for the gradient. So as a rule, your data points should cover more than half the paper in both directions, and they will be looking for that. They will also, by the way, if you are ever asked to find a gradient, I am so ruthless about this. And you can check my stream from this morning about how I did a similar thing. But you want to make sure that you are drawing the biggest possible triangle such that the corners of the triangle are in precise spots. So let's say I draw, can I draw a straight line? Let's draw a random straight line like this. So if I were using this, you can't really see the subdivisions very, very well. OCRA. But you would want, so how would I, if this was my thing, how would I draw a triangle? I would want it to be as big as possible going through. So this point here is smack bang in the corner of that square. So I can use that point. And then I look at the other end, and that point there, right near the end, would again be smack bang in the corner of a square. So what I would do is I would draw my, oh God, no, why is this happening? Tech is teching and I hate it. All right, so I would draw something like that. And then I would draw something, no. And I would, no, just let me draw a new line. Oh wait, I'm not clicking on the right thing. Oops, my fault. User error, user error. Okay, something like that. So this would be a huge triangle, obviously. You want your triangle to cover at least 2/3 of the paper. They have strict requirements that it has to take up enough of the vertical axis and enough of the horizontal axis. But again, my advice to you is to make sure you are very, very selective about where you draw your triangle. Because if you're even a little bit off, you would be so surprised how that uncertainty could just like explode your gradient calculations. And they have ranges. And if you fall outside that range, you're done. So In conclusion, your choice of axis should enable your data points to cover at least half of the vertical and the horizontal scales for whatever you choose. They should be regular intervals that are easily subdivided. You are allowed to truncate if your data does not cover the full available space. When you are doing your triangle, make sure that the ends of your triangle are precisely in corners of subdivided squares so that you can get very, very accurate readings for delta y and delta x. And your triangle should be as big as you can possibly make it, but certainly bigger than 2/3 of the page. Do you think you should do data every 20 squares or in 10? It's honestly, what you should be doing is making it fill the page. So if you had grid paper which had, so let's say you had values covering between 0 and 100. Is that the best? What do I want to do? Okay, so let's say I had A values and B values. And let's say my A values went between 10 and 80, and my B values went between 0 and 120. And let's say I had grid paper which went 15 square, let's say it was 15, 1, 2, 3, 4, 15 by 10. Broke my own rule about doing threes, whatever. Okay, so let's say I had grid paper that looked like this. You kind of have a choice when you're doing this, like about which orientation to put the grid paper. I would choose an orientation that allows you to make the most of the available axes. So in this case, it might make the most sense to put B on this axis and A on this axis. Now, obviously, if A is the independent variable, you can flip that round so that A is still on the y-axis. But because B has the bigger range, I would probably want to put B on the bottom. That said, if there were exactly 12, so for instance, if this was a, what did I say it was? If this was a 15 by 10 paper, for instance, then that might be how I choose to arrange it. So I might have my B's go in every 10 from 0 up to 120, covering most of that side of the paper. And I would have my A's go from 0 to 80, covering most of that side of the paper. So that landscape orientation would be perfect. If instead I had paper that was say 16 by 12, you could instead argue that it would be better to have the B there if that was 12 and that was 16, and then go up in 2 increments. So it would be 10, like 20, et cetera, et cetera, et cetera. Because then you're using maximum space, just whatever way you orient it, so you can make the scales as big as humanly possible. So here you would just be able to fit A on the vertical and just be able to fit B on the horizontal. So it's surprisingly thought-inducing trying to do that. I remember spending ages at university trying to think of the perfect orientation and the perfect scale. But the basic idea is just play around with your options. Like, what are my options? What can I do? How can I maximize the scale and the orientation so that this paper gets filled? And that includes truncating, by the way. So you'd be surprised how much work you've got to do on this. You think it should be easy. It's not easy. So thank you so much for reminding me to talk about that. Well, the main reason I didn't actually is because I did a paper this morning, and you don't typically have to draw your own graphs there. It's more of a university thing. But you are so right that is very, very important in experimental physics. I am told that my battery is low on speaker, but it's all right because I don't need to hear you. You just need to hear me. So you are very welcome for that. Thank you for dipping in right at the end and making me talk about good things. Hopefully that helps. And if you have any other questions, feel free to leave them in the comments. I will absolutely answer them there. As always, feel free to recommend videos and I'll sort of go through them live. And now you have seen the benefit of dropping in live and poking me to talk about good things, because lesson planning is not my thing. What is motivating you? Honestly, I just like the motivating me how? I think for me, because let's be real, the content itself, like it's interesting, but that's something I did like decades ago, a while ago. So like that itself isn't the thing that interests me. Right now, the thing that's interesting me is how I communicate myself. So that's why streaming for me is a very interesting challenge, because before I was sort of morphing myself to a student, like communicating it in a way that works for them. But if I didn't get that feedback, I was like, oh, how do I know I'm doing it right? So for me to sort of stand here and kind of communicate the way I'm going to communicate it, the way I think it needs to be done, and to not rely on constant validation from a student that I'm doing a good job, that's kind of motivating me. Like, how can I kind of be adaptable, flexible, have people throw things my way and me sort of like build them in and sort of like work on them? How do I meet sort of these sorts of like ever-changing challenges while still communicating myself in a way that is both engaging and accurate and like doesn't trip over my own words? That kind of side, that linguistic communicating side. What's motivating me to stream alone? Well, also my initial motivation was it was the entrance test. So I started this in September because I had students who were going in for entrance tests for Oxford and Cambridge, and the papers required such specific exam technique, especially the ESAT, which is 90 seconds a question, like balls to the wall, max out sprint, nonstop, no time, go, go, go. Like I was like, no, do this, but do this. But I was like, okay, screw it. I'm just gonna like show you. So I was like, watch me do a paper now. So I put a stream out because it was easy because I didn't have to edit it. And I thought, okay, if it reaches some other people, cool, whatever. And it reached a few little people, and I was like, yay, okay, that is helpful, right? So yeah, so that's why I kind of keep to this sort of system. And then once I started the Cambridge interview series, that's when I started these evening streams where people were popping in and asking me direct questions. And I'm keeping this format of like a live solve a week and an evening stream where I get to actually interact with you guys more directly, because I think it works and it's kind of just sort of interesting for what I want to do. Definitely watch the rest of it. Seems perfect for all of us. Experimental physics. Great. Glad you're enjoying it. Yeah, feel free to keep dropping comments. And I think I'll leave it there, but I'll keep an eye out, as always. Like I read all the comments because there are enough that I can keep track of them. So yeah, watch the space, and I'll see you guys next week. So I hope you guys have a good week. In the meantime, work hard, have fun, and I'll see you next time. All right, take care. Bye-bye.